6 years ago, the modern horizontal axis wind turbine HOT was made. Today, there has been little innovation in the field of wind energy, along with many wind farms being taken down for living space. As stated by the American Wind Energy Association, the estimated U.S. wind energy potential is about 10.8 trillion kilowatt hours per year, which is equal to the amount of energy in 20 billion barrels of oil. Our goal is to expand the area where and how wind energy can be captured to bring in a new era of clean energy. We decided to bring the field of wind power to the city. According to the U.S. National Weather Service, winds in cities average around 12 miles per hour, with gusts that can go up to 20 miles per hour. But due to the many buildings, wind patterns are different. There are downdraft effects, venturi effects, and eddies throughout the cities. The modern turbine would not be efficient in these conditions, so we looked into the vertical axis wind turbine. FOTs are smaller than modern turbines and require very little maintenance. Since they are on a vertical axis, they do not need to turn to the direction the wind is coming from. Looking deeper into the VOT design, there are two main types, Darius and Savonius. The Darius is a more rigid build and relies on wind lift to spin. The Savonius is a lighter VOT with slender blades that rely on drag. These two types of VOTs sounded promising, so we considered both ideas. Our next step was setting the criteria for our designs. To start, we made a small-scale model of a HOT and it produced 5 milliwatts. We wanted our prototype to surpass this, so we set our first criteria for our design to produce a minimum of 5 milliwatts. Another key factor of the wind in the city is the chaotic wind patterns. For this, we decided our second performance criteria would be its versatility, where it can take wind in from any angle. Our third criterion we chose was durability. Cities have strong winds, and our prototypes had to be able to withstand them while capturing their energy. They also need to be sturdy to prevent damage from foreign objects.
Based on this design criteria, we entered the ideation process, where we used the research as a guide in order to come up with designs that would meet our criteria. Once we came up with the possible design, we used Fusion 360, a CAD software, in order to model the designs in 3D. After that, we ran simulations which are available in Fusion 360, such as CFD simulations and a stress simulation, to find out how our turbine might perform. Based on this, we made some adjustments and printed our turbine. After that, we tested our turbine in a testing apparatus. We tested from 90 degrees, 30 degrees of depression, 45 degrees of depression, and 60 degrees of depression. This allowed us to not only measure the power output of the turbine, but also the versatility of the turbine. Next, in order to see if our turbine would meet our third design criteria of strength, we tested it with the air compressor and with a drop test, where we dropped the turbine from a height of 5 feet and we shot it with the air compressor at 135 miles per hour in order to see if the turbine would survive at high winds. Based on the results of our test, we entered the redesign stage. We looked at what criteria the turbine didn't meet, and we looked at research to see why it didn't meet it.
We started our design process with the white print. The purpose of this design was to act as a benchmark for any data we would get from future designs. This design was relatively efficient, however, it was bad at capturing wind from different angles. From the white print, we moved into the two main types of vertical axis turbines, which are Savonius turbines and Darius turbines. The concept of our pink print, which was our Savonius design, was that it would create pockets to capture wind moving at upward and downward angles. This design was inefficient, however, the results from all the angles were very similar. The idea behind our Darius type design, or our light pole design, was that it was light and therefore easy to spin. However, it was inefficient because it had very little surface area. It was also not versatile and could not capture wind from different angles very well, and that was our only design that did not meet our durability criteria, as it broke during the drop test. Because we had not been successful with these 3 turbines, we went back to researching. Through our research, we found that the more surface area there is in each blade, the more energy would be generated. The idea behind the curved blade is that it has more surface area than the flat one in the same amount of space. Another advantage of the curved blades is that the 4th blade would block these winds from creating negative drag. Because of this design came very close to the efficiency criteria, but it did not capture wind from different angles very well. Moving forward, we wanted to increase versatility, so we looked back at the pink print because we liked how the numbers across all angles were similar. We used the same concept of creating pockets for both downward and upward angles, but also implemented the curve for maximum efficiency, and this design, which we call the hourglass, greatly exceeded all of our design criteria.
Now that we had a design that met all of our design criteria, we looked into how we could implement the design in the city. The first thing we looked at were where are the best places that we could put the design in the city. Because putting a wind turbine in a city is a new innovative idea, there were no resources out there about wind in cities, so we created our own. We ran CFD simulations on 3D models of cities in order to find where the best places to put the turbines were. We then created a program in Python to compile all of this data and mark the locations. This allows us to easily find places to put turbines in cities.